showing the screen yet of my laptop? Not yet. What the heck? Now? Oh. Now? Oh dear. Now? Whoa. Ah, come on. This cable is a bit fussy, isn't it? Oh, I remember what I did last time. Didn't I have to plug in the computer directly into it, isn't it? Maybe that will work. Great. Andek or Matt, do you mind just turning this a little bit? It's a bit to the left. Well, what those guys think, is that alright?
Yeah.
Okay. I was saying to Andek, I absolutely have to do the experiments on Monday. I keep delaying it, and well, that's because there keeps being problems, but I have to do it on Monday. Don't let me not do it on Monday, okay? So when Monday comes around, if I say we'll have a class, just, pin me to the ground and say, no, we're doing the experiments. You have to do them on Monday.
Next Monday? Yeah.
Yeah. Yeah. It's the only class in the week that's not at 9 o'clock, right? Right? I think this would be the best time to do it. Agreed?
Yes.
I think doing it at 9 o'clock would be a bad idea. True? True, yeah, okay. So, we'll start the final chapter, which is atoms. Now we're doing quite well. This is it's kind of the middle of March, near to the end. So we still have at least 2 full months. So my goal is to get the labs and the book finished in 1 month, and that will give us 1 month for revision, which I think is actually quite good, right? So if we get the labs finished in 4 weeks, so we'll do it on Monday, and then we'll take maybe 3 weeks to write it, so that's 1 month, and then we should have the book finished in 1 month, and then we have 1 month free for revision, 4 weeks. I think that's good.
Yeah.
2 weeks, no, 4 weeks. 4 weeks, how many classes a week? Six classes a week, isn't it?
For physics.
Yeah. Yeah, it's 6, isn't it? 2, 2, 2. So that's 24 revision classes. So we'll get to do maybe 10 exam papers, maybe 9. I think that's good. So we'll look at the last chapter now, which is called Atoms. And this is nice for you because you also study chemistry. So some of it actually will be easy for you. Some of it. What are you doing in chemistry? What are you doing in chemistry at the moment?
Chemistry.
Yeah, you know that subject you do, chemistry?
Yeah.
Too long ago, huh? Like 4 days ago. Oh, by the way, did you all have a good St. Patrick's Day? Did anyone go see the parade?
I didn't. A bit disappointed.
Bit disappointed. Halloween was better? Really? What made it better? The fireworks? Yeah, yeah. Oh, the floats were better. Okay.
In the studio set, I think they are a lot of orchestra.
In where?
The parade.
Yeah. You don't like this?
Not
You-
interesting.
You prefer the floats? Yeah. Okay. Fair enough. Fair enough. Did you see it on there?
I've seen it on his Instagram.
On his Instagram. Okay. Did you go to the parade, Joe? You stayed at home? Okay. You sleep?
No, I work at the weekend.
Oh, you were working. What do you do?
Floor,
Huh?
floor, like in the Chinese restaurant.
Ah, Chinese restaurant. Waiter. Oh, great. Okay. You get tips?
Yeah.
Tips are good.
Tips are good.
Yeah, yeah, okay.
And sometimes they
Very good tips.
just say.
It's okay tips. Good, 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 good. Okay, let's start now. Nuclear decay. We're starting atoms. You got this? Nuclear decay? You look cold.
Yeah,
You sick?
I don't see it.
You got that, guys? Nuclear decay. Yeah? Okay, so. I don't. Let me just check something here, sorry. Yeah. Have you ever heard of this radioactive decay? I don't know if you did it in chemistry.
We did in physics.
You did it in physics before, yeah. So, not chemistry.
No.
Radioactive decay, also known as nuclear decay, or radioactivity, I'll call this, is the process by which a nucleus of an unstable atom loses energy by emitting ionizing radiation. Now, you know the word ionizing. You did ionizing in chemistry, right? The types of radiation are alpha, beta, and gamma. So, you know, you have some nucleus, and what happens is it loses energy, and the energy comes off in 3 different ways. It comes out as an alpha, a beta, or a gamma. Okay, and the radiation is ionizing. Now you know this word from chemistry, don't you? Ionizing. So the energy that comes off, you could use it to ionize atoms. Do you know what I mean? Like, so if you had another atom and you had an electron around it, and some alpha energy came off here, or beta or gamma or whatever, it could ionize the electron off of this atom. Okay, that's actually important because that's what makes it harmful to your health, is that it's ionizing. So when the radiation hits your hand, it could free an electron. That's actually what makes you sick, because then the electron, well, we'll talk about it later, but the electron could hit into your DNA. So anyways, we'll come to that later. So the important thing here is it's how it loses energy, and the 3 forms are alpha particles, beta particles, and gamma rays. Okay, so I'll just give you a minute to write that definition down. Got that? Great, okay. So a good example is uranium-239, and this is an isotope of uranium. Have you looked at uranium in chemistry? In chemistry class? No, okay. Uranium-239 decays, that is, alpha, beta and gamma will be released from it. And uranium will not do this forever. So if you have some uranium and put it there, over time, alpha, beta and gamma radiation comes out. But it won't do it forever. It'll do it for some, actually I'll have to check it, it'll do it for some while. But we'll talk about that in another class. Okay, so I said there are three types, alpha, beta and gamma. You said you've seen this before, and alpha, beta and gamma. Or you heard of it before? Yeah. Matt, you've heard of these before, alpha, beta, gamma? Yeah. Do any of you know what exactly alpha is? True, it's positive, yeah. But what is it made of? You are right, it's positively charged. How many? Oh, no. 2. Okay, yeah. So, alpha particle consists of 2 protons and what else? What else? How many neutrons?
1, 2, 0.
0, 1 or 2, correct, one of those. 2 neutrons. And no electrons. So, as Matt was saying, it has a positive charge. And you realise they're stuck together, so they look like helium. You know, because helium is 2 protons. So it's actually really, it's a helium isotope. You got this, Andek? Yeah. You got this, Matt? Continue? Okay, so the next one is, oh, and sorry, the symbol is, of course, alpha, or another way you can write it is as helium-42. This is what you use in chemistry class, isn't it? Right? Yeah?
Yes.
What's the meaning of the 2 here? Yeah, so what's the mass number? What does that mean? Number of protons, yeah. Oh no, that's not called the mass number. What's the 2 called? Not the mass number, the atomic number, isn't it? Or the mass number is the 4, isn't it?
Yeah.
Yeah, and what does the 4 mean? Yeah, which is the number of protons and neutrons. That's called the mass number, and I think that's called the atomic number. Anyways, they're the 2 symbols, okay? Right, do any of you know what the beta particle is? What is it? Yeah, so what do you think it is? It's good, yeah. The beta particle are high energy, that means high speed electrons. And the symbol, well, you know the symbol for beta, don't you? The symbol is that. Or, now, tell me, in chemistry, how do you represent an electron? What symbol do you use? Yeah? E, but what numbers do you write? Or you don't? Yeah, where do you write it? Top, bottom? Ah, top right, yeah. That -1 is for the charge, isn't it? Yeah. In physics, we put it in a different place, which we'll see why later. So we write the electron like this, a -1 and a 0. Got that? Okay. And the last one is gamma rays. Now, gamma rays are basically high energy waves, kind of like X-rays. They're high energy electromagnetic waves, and the symbol is gamma. And if you want, sometimes people write gamma here and then a 0, 0 if you want. Okay, you got that? Yeah? You got that, Joe? Yeah? Okay. So, Newton's first law tells us that the atom should not just decay, that a force must be acting. So you know Newton's first law says an object will remain at rest unless acted on by a force, right? Okay, so if the atom is just sitting here doing nothing, and then all of a sudden an alpha particle comes off and a beta particle comes off, it can't just do that. There must be some force that pushes the particles out. Do you understand? Do you know what I mean? Like, you would be quite shocked if this was sitting here and all of a sudden it just moved by itself. Because you know Newton's first law says that there must be a force to cause it to move if it's at rest. Yeah? So, same thing here with the decay. The alpha and the beta don't just magically leave the atom. There must be some force that causes them to leave. And this force is called the weak nuclear force. This is the force that pushes the alpha and the beta out of the particle, out of the nucleus. Now, there's a reason why it's called weak, because most of the time it's not strong enough to push the particles out. That's why most of the time most nuclei are stable. You know, like in chemistry, a lot of atoms that just stay there. It's only some atoms that decay, where parts fly off. The big atoms like uranium. But most things are stable. So the weak nuclear force, in the exam, they usually ask you to give 3 things about the weak nuclear force. So the 3 things you could say, firstly, it's weak, which is easy to remember. So that's number 1, it's weak. Another thing you could say, it's a repulsive force, meaning it pushes things out. Okay, that's number 2. And number 3, it acts over a very short range. So it only has a range of 10 to the minus 18 meters. And it's the force responsible for nuclear decay. So there's 4 things about it. In the exam, they usually ask you for 3 things about it. So they might say, state 3 properties of the weak nuclear force. I think it'd be a good idea in your definition to write, just to help you remember here, like the number 1, 2, and here acts only in the nucleus of an atom over a very short range, 3, and then it's a force responsible for decay. That could be 4. So there's 4 things there about it. Okay, so you might wonder if there's some counterbalancing force, and the answer is we'll have a look at that later. So there's a force that pushes out, but there's also a force that pulls in as well. That's a different thing later. Okay, so a few more definitions, I'm afraid. The proton number, we call that letter Z. And you probably know this from chemistry. What's the proton number of an atom? So for example, what's the proton number of hydrogen? 1. Okay. And oxygen? Or well, maybe that's hard. Carbon? 6 is carbon. And lithium is 3? Isn't it? Yeah. Helium is 2, and so on. So the proton number of an atom is the number of protons in the atom. This defines what the atom is. So you know from chemistry, the number of protons tells you what the atom is. So if it has 1 proton, it is, if it has 1 proton, it is hydrogen. If it has 2 protons, it is helium. So the proton number defines the atom. For example, 1 proton makes the atom hydrogen. 2 protons makes it helium. And we can look up what an atom is from the periodic table, which you all have from your chemistry class, right? So you just need to write the first sentence, or the first 2 sentences here. This is, in the exam, there's usually a question for like 1 mark. What is the proton number? You got that, guys?
Yeah.
Yeah? Continue? Yep, great. Okay. Right, what's the nucleon number, A?
Is it
Yeah.
neutron number?
Yeah?
Neutron minus?
Oh, no. Not as complicated as that. It does have to do with the neutron and protons, though. It's just plus. It's the number of protons and neutrons in an atom. Huh?
Isn't that mass number?
It's the same thing as mass number, yeah. Yeah, you're right, it's the same thing as mass number. Okay, so you can write that down, that'd be great, please. You got that? Got that? Okay. The atoms of chemicals that can exist in different types, these are called isotopes. So what exactly is an isotope?
Same atom but different proton number.
Oh, I think you got it backwards. Say again?
Same atom but different
Di-
neutrons.
Different neutron number, yeah. They have the same number of protons, but a different number of neutrons. Different isotopes of the same elements have different masses. Yeah? So here's some examples. This is hydrogen, 1 proton, no neutrons. This is hydrogen, 1 proton, 1 neutron. and this is hydrogen, 1 proton, and 2 neutrons. These are all isotopes of hydrogen. Yeah? These all have special names actually for hydrogen. What's it called? Like deuterium? Do you do this in chemistry as well? No, okay, fine. Anyways, you know isotopes from chemistry. So if you can write this definition down. Andek, did Siba or Kim reply to you on WhatsApp? Because usually Siba's like the first one here.
No.
No, okay.
Every one person see my message. It's a format. Yeah.
Okay, okay. Got that? Yes? Sure. Okay. Just tell me when you have it. Were you working over the weekend, Matt? Oh, you didn't have extra hours. You just normal Sunday hours. Yeah. Okay. Okay. So you didn't have a busy weekend. That's good. You got that?
Yeah.
Okay. Right. Okay, so we talked about that. Oh, and of course the extra neutrons make the hydrogen heavier. Okay. Now, this is interesting. This is called the penetrating power of alpha, beta, and gamma radiation. Okay, so interestingly, if you had some alpha radiation, you could actually block it with your hand. So if the alpha radiation comes off of this, you can actually stop it with your hand. So it doesn't really penetrate. It can't really push through things. Okay, beta can do a bit better. Beta will travel through your hand, but you could stop it with, you know, some piece of metal, piece of aluminium, you know, like what have we got here? I don't have any piece of metal. Nothing. All right. Like a not too thick, maybe a couple of millimeters of metal. Yeah. So you could stop it with aluminium. Gamma will go through your hand. It will go through metals. In fact, it will go through most things. And to stop it is quite difficult. You need a big piece of lead, like a big piece of lead, maybe like this much. Okay. Or I think you can also stop it with 1 meter of concrete, of stone. Okay, so gamma can really penetrate, really push through. Okay. Whoops. The good news, the one that's most harmful to your health, do any of you know? No, actually it's alpha. I know why you think gamma, because it goes through. Alpha is most dangerous to your health, but you can easily block it. If it ever got inside you, you know, if you swallowed it or something like this, that's very bad, very, very bad. Okay, you maybe see them on, you see the people on the movie wearing the suit. You know what I mean? Like the radiation suit. That can stop alpha. Can stop maybe some beta. It wouldn't be able to stop gamma. Okay. So what you could do, you can either draw this or you could just write it in your notebook. Because in the exam they might ask you a question like, what would block alpha? So even, look, guys, even a sheet of paper would block alpha. It would just hit off the page. Okay, alpha is really easy to block. Your skin would block it. Okay, beta, you need a piece of metal, like a sheet of metal, piece of metal. And gamma, you need like a big piece of lead. Okay, so you can write or draw this fact. Got that? Yeah? Not yet? Got that? Are you sure?
Yep.
Okay. Continue? Yeah? Right. So, let's look in more details what this notation means. I'll just take a minute. It's not really necessary. So, when you write something like this, what does the X represent? What usually is where the X is? The atom's name, yeah. So, like, hydrogen would be what letter? H. Lithium? Li, yeah. What's the A? Nucleon number, yeah. And the Z? Proton. So all I want you to do to write in your notebook is to write this and then just put the names beside it. So beside A, write nucleon number. Beside Z, write proton number. And beside X, write the atom's name. Yeah. The A is the nucleon number. Z is the proton number. And X is the atom's name? Got that? Okay, continue. Okay. During radioactive decay, there are 4 quantities which are conserved. They are. So, remember the word conserved means it doesn't change. So what are the 4 things that you think doesn't change? So the first one is energy. So the energy at the beginning equals the energy at the end. Okay? So the alpha particle comes off. The energy here plus the energy here equals the total energy at the beginning. This is called the conservation of energy, where we looked at this a couple of times. Momentum is also conserved. You know this too? Conservation of momentum. So what happens when the alpha particle is released, this actually moves backwards a little bit. So you know the m1u1 plus m2u2 equals m1v1 plus m2v2. You remember this formula? Yeah. Thirdly, charge is conserved. So for example, the alpha particle, what charge does the alpha particle have? Plus what? Plus 2. So if this has a plus 2, then the charge here reduced by 2. Yeah? Because conservation of charge. What's the last one before I tell you? What else do you think is conserved? See, it looks like we have all the big ones here, doesn't it? So the last one which is conserved is the nucleon number. So the nucleon number at the beginning will equal the nucleon number at the end. So for example, if this had a nucleon number of whatever, 100, 200, whatever, and afterwards an alpha particle is released, what's the nucleon number of an alpha particle? You can look at the definition if you don't, not sure. What's the nucleon number of an alpha particle? 4. So, if this guy comes off with a 4, then what happens to the nucleon number here? It's reduced by 4. Do you understand? So, you need to make note of this. These are the 4 things which are conserved in decay. Okay, you got that? Okay, no problem, no problem. Yeah, got that? Okay. Right. So, some reactions here. Since alpha is 2 protons and 2 neutrons, then the decaying material will see its number of protons and neutrons decrease both by 2. So for example, here we have our material, and let's say, I don't know, whatever, it has so many protons and so many neutrons, P and N, and then out comes an alpha particle, and the alpha particle has 2 protons and 2 neutrons. Okay? So then what happens here is this guy loses 2 protons and loses 2 neutrons. Obviously. Fair enough? Right? Makes sense? Yeah? So that's obvious. That's alpha. Beta is a bit strange. So with beta, an electron comes out. So if this has e electrons, then what happens to the number of electrons? Well, it loses one, right? Right? Yeah? What's wrong? It's okay? Or yeah. So if an electron hops out, then the number of electrons left will be just minus one, because it lost one. Yeah. So if it had 100 electrons and one electron leaves, it has 99 electrons. That's fine. Now, what's strange though about the beta particle, since beta is one electron, then the decaying material will see its number of electrons decrease by one. That's obvious. It's fine. But what's really strange about beta, oddly, one neutron will become one proton. This is very strange. So, a neutron that was in this material will now turn into a proton. Very strange. Very, very strange. Yes? So, when a beta is released from a material, you lose an electron, fine, that's okay, and this happens, which is very, very strange. A neutron converts into a proton, which is quite amazing, as I bet you didn't know that neutrons could change into protons. I can tell from the look on your face that you're quite shocked, right? So that's very strange, agreed? Yeah. And the last one is gamma. Yeah, it's quite weird, but it does happen. Trust me, it does really happen. Gamma has no particles, so nothing is changed. So gamma is just a wave. So there's no change here. Still the same number of protons and electrons and neutrons. Okay. So I need you to write this down. Now, you don't have to write every single word down. You can just write your own key point. So like for example, in number 1 you could just say, in alpha the number of protons and neutrons reduced by 2. Say something like that. In beta the electrons reduced by 1 and a neutron becomes a proton. And number 3, gamma, no change in proton and neutron number. Okay, so whatever way you want to write it. You got that? No, no, just let me know when you have it, no problem. You have that, Max? Yeah? Okay, great. Chad?
1 second.
No problem.
Oh, Kim had this exam prep today. She has it on timetable, hang on.
Was she looking at Monday's class or something?
No, because we had a change in timetable.
Ah.
And
So she thought exam prep, screw it.
because the exam prep starts at 10.
Oh, okay, fair enough. Oh, so she might be here for the second class?
Maybe.
Okay,
So I'm sending her the new timetable.
good idea. Got it, thank you. Okay. Let's have a look at this example. We'll need the calculators. A small amount of uranium, 0.01 nanogram, is undergoing radioactive decay. So what I have is 0.01 nanograms, which is equal 10 to the minus 14 kilograms, I think. I think so. Is that right? I hope so. Nano is 9, isn't it? Yeah. Okay, so it's undergone radioactive decay. Represent this decay as a nuclear equation. So what happens is you start off with uranium 239. Now I don't have my periodic table. Do you have it with you? Can you tell me what the proton number is for uranium? What is it? 92, okay. So in this example, the uranium releases some alpha, which is helium-42. Now, I'm sorry, I didn't actually say it in the question. Let me just see. Let me just check something here. Yeah. So the uranium just releases an alpha particle. I need to change this question a little bit. Anyways, so the uranium releases an alpha particle. Now, what happens to the nucleon number? If it was 239 beforehand and afterwards it loses 4, what is it now? 235, very good. And what's the proton number? 90. So, can you check what atom that is? 90 on your periodic table. I think it's thorium. Yeah, it is, yeah. Okay, that's part 1. Part 2. What is the velocity when the alpha particle is released with that speed, 0.05 c? So what happens is this. You have the uranium at the start, And then afterwards you get thorium and your alpha particle. And the alpha particle moves off this way with a speed of 0.05 c. And the thorium moves backwards with a speed of, we don't know, we'll call it v. And I need to know what the v is. And this is at the end. Is that okay so far? Yeah? Right. Now, we know the mass of the uranium, because I give it to you in the question. There it is there. So what formula do I need to help calculate the v? What formula could I use here? Yeah, what's that called? Conservation momentum. So, m1 u1 plus m2 u2, that's basically 0 at the beginning. That's equal to m1 m1 v plus m2 v2, which is 0.05 c. Okay. Now, what's the m1 and what's the m2? Let me just make a bit more space. Okay, the m1 we know, it's 10 to the minus 14. Oh, we don't know the m1. It's 10 to the minus 14 minus. Now, do you see this thorium here? Its mass will be less than the uranium. So it's not quite 10 to the 14. What do I need to take away from 10 to the 14, minus 14? I should take away the mass of this guy, because he came out of this. Do you understand? So it's like if I had this here, imagine I know the mass of the bottle, and then the lid comes off. Then what's the mass now? It was the mass at the beginning minus the mass of the lid. Yeah? So what was the mass at the beginning? It was 10 to the minus 14. Now what's the mass of the alpha particle? Well, what is the alpha particle made of? It's made of 2 protons and 2 neutrons. So I just need to take away the mass of 2 mass protons and 2 mass neutrons. Now, I gave you these masses in a previous lesson, but I think they're on your calculator. Chow, I think these are constants 1 and 2. Plus mass of the alpha particle. That's 2 mass proton plus 2 mass neutron times 0.05 times c. So, oh, and v is here. So therefore, v will equal minus 2 mass proton, sorry, I should say neutron, plus 2 mass neutron times 0.05 times c over 10 to the minus 14 minus 2 mass proton minus 2 mass neutron. Now I think this will be quite a small number. Are you working it out, Matt? This here? You got that? got that? Got an answer? Got that? C is 3 times 10 to the 8. Speed of light.
How do you do better? MP and
They're not on your calculator?
No.
I gave them in a lesson. You know, actually, I think when I gave them to you, I gave them into the lesson on materials in semester 1. So if you don't have them handy, those calculators have them built in, I think, don't they? Yeah, so what answer did you get, Matt?
1 times 10 to the power
10 to the minus 5. What did you get? Error? Can you pass it up? Let me have a look. Error, huh? Yeah. I think here perhaps you need to multiply. Come in! Who have I got? Well, look who it is. Yeah, no, it's right. You just forgot to type and multiply. 10 to the minus 5. Okay. Continue. And that. Let me just fix this question here at the back. So. Okay. So the last thing in this question I want to calculate is how much energy the alpha particle has. How much energy. So what type of energy does this guy have? It only has kinetic, isn't it? So the kinetic energy, which is the energy, is a half mv squared, which is a half 2mp plus 2mn times the v squared, which is mp plus mn times 10 to the minus 10. Okay, so if you just put that in, please. Yeah, so what would be good is if you convert into electron volts by dividing by E. Got that? What did you get?
2 times 0 times 10 to the power negative 80.
Negative what?
80.
Negative 80?
18.
18? E? Is that, okay, what was before you divided by E?
3.35 times 10 to the power negative 37.
Yeah, okay, that is very small, yes. No, so there's no, okay, there's no point in converting it into E because it doesn't, it's still very small, so we'll just leave it like that. Oh, no! My mistake. What's wrong here? The V. What's that the speed of? 10 to the minus 10. That's the speed of this guy. I wanted the speed of this guy. What's the speed of this guy? Yeah, it was the 0.05 c. Sorry. So I put the wrong number here. Apologies. That's why it was so small. 0.05 c squared. Okay. Let's try that again. That's better. So if you convert that into electron volts, what do you get? It's probably a big number now. Mm-hmm. 46945 electron volts. 1, 2, 3, 4, 5, 6. So that's 4.69 mega electron volts. Okay. So, Kim, you thought it was exam prep at 10 o'clock today. Is that what you have on Wednesday?
No, it's supposed to be on Tuesday.
Today is Tuesday, isn't it?
No, in the old timetable, but now
It's now changed, yeah. Yeah, okay. Okie dokie. Continue? Yeah? Okay, just, you got that? Yeah. Right. How many alpha and beta particles are released when uranium decays into lead? So let's have a look at this equation. You have uranium 23592, and that turns into lead 20782, because there were X number of alpha particles released plus Y number of beta. So what's happened here is you have uranium and then later it becomes lead after it releases some alpha and some beta. It became lead. Okay? The question is, how many alphas and how many betas? Right? So I'll call it X and Y for X alphas and Y betas. Is that okay? Now the way to solve this is actually quite easy. It's a good exam question because we have to just use the fact that the nucleon number is conserved. So what that means is 235 should equal, tell me what you think, 207 plus,
X times 4.
very good, X times 4, 4X, plus 0Y, excellent. And then 92 should equal what?
82 plus 2x minus 1y.
Very good. Now, you realise that this is quite easy to solve, right? Like the first equation gives you 235 minus 207 divided by 4, that's equal to x. So what's that,
7.
please? Is it 7?
Yeah.
You're confident?
Yeah.
Okay. 7. Now, we can sub that in here to get the y. So you have 92 equals 82 plus 14 minus y. So y equals 4. Y equals 4. Yeah? So that means uranium became lead with 4 alphas and 2 betas. Oh, sorry, not 4. What am I saying? 7 alphas and 4 betas. Not difficult, right? It's actually a nice exam question when they ask you to balance. Now, you're probably quite familiar with balancing equations in chemistry, right? You've probably done it a lot. This is done a little bit differently in physics, but I think you agree that it's not really, oh sorry, can you see? It's not really that difficult. Yeah? It's okay? Like really the idea is simple. You just make sure that the top here equals the top here, and the bottom here equals the bottom here, and that's it. Balanced. Okay? Now sometimes you might get a gamma, but you don't know how much the gamma is. So if you want, you can just write plus gamma at the end. Yeah, easy peasy? Easy peasy, I think. So if you look at the workbook, all that you really have to do today is just balance the equations. Now maybe I'll do one more. No wait, before we look at the book, let me just do one more. Let's see. Balance nuclear equations. Let's give an example of one. Okay. Let me give you what an interesting one. No, okay, I'll give you a boring one. Sorry. Okay, let's try and balance this. You have no, sorry, it's too boring. I want to make it a little interesting. Boring. Okay. I'm sorry, I just have to give you a boring one. Here we go. Uranium 23592 plus a neutron. So what that means is you have some uranium and you fire a neutron at it. This becomes whatever the heck, what's Xe? Oh, neon? So, what's Xe? Xeon? What's it called? Yeah. Do you know what it's called? How do you spell that? Xeon.
No,
Xe. The heck is that? Okay, anyways. Xe. Xe plus 2 neutrons plus you don't know how many alphas and you don't know how many betas. And I want you to figure out how many alphas and how many betas. Okay? I'll give you a minute and then we'll do it together. You'll need your periodic table because you'll need to look up what this number is. I'll tell you what, I'll give you this number. It's 135. But you'll need to check what this number is. Yeah, this is an isotope, I guess. It has an extra 4 neutrons. Got an answer? Right here.
Beta is 0 and 1, right?
-1.
-1.
Mhm. Got an answer, folks? Is that yes or no? My goodness, okay. It's taking a bit longer than I thought. Yeah? Got an answer, Matt? Okay, so first question, folks. What was the number here, the proton number for XE? 54. So, and here, this was X alphas and Y betas. Yeah? So, 235 plus 1 should equal 135 plus 2 plus 4x. Did you get that? Good, good. So what did you get for x then, Andek or Chow or anyone who got it?
4.75.
Point!
Yeah.
Oh no, that's tragic. That's tragic. 34.75.
24.75.
24.75. 24. That's terrible. Are you sure?
Yeah.
Let me check something. Ah. That's not supposed to happen. I guess where I got this question from wasn't reliable. You're not really supposed to have a decimal number here. So I think maybe they made a mistake. Does the problem go away if you change this to?
Maybe the number of neutron number, for example.
Maybe you think this was wrong? Yeah, maybe it was.
So if we would change the 134, right?
Would it work if it was 134?
Yeah, I think it would still be. Yeah, it will work.
Okay, let's do that. Yeah, I'm sorry, it's in this example here they have 135. The only problem is I have to pay if I want to see the answer. So we'll change it just to 134. Okay, so what did you get for x now? Better. Okay, 25. Right. 97 plus 0 should equal 54 plus 0 minus y. So what did you get for y? Y should be the same. What did you get? Oh, sorry, I missed my 54 plus 0 plus 2x minus y. Okay, so what did you get for y? 7. Yeah? So that means if you have uranium and you add a neutron to it, then that will become Xe plus 25 alphas plus 7 betas. I wonder what went wrong with this. Oh well. Oh well. Maybe I'll have to find out. No. I don't think I'll find out unless I pay to subscribe to the website, which I of course don't want to do. Yeah. So these questions come up in the exam and they're actually very nice in the exam because usually you get for a question like, well, tell me what you think. How many marks do you think getting the x and the y is here? Yeah, it's a 4-mark question in the exam usually, which is pretty good because really all you're doing is solving a simultaneous equation for maths class. Yeah, so I think what they usually do is they give you like, oh, I can't remember, it's something like you get 2 marks for writing this and then 2 marks for the answer for x and y or something like this. So it's a 4-mark question, so it's pretty good in the exam. Okay, now Kim, you missed the first lesson. I don't know if this is all very confusing, probably. You'll have to watch the video, I think. There's 10 minutes left, so that seems like a good amount of time for you to get these questions finished. And then what we'll do next time, when's our next class? We'll have another lecture and then we'll do a tutorial on the answers to this. Okay? But I don't think you'll find these difficult. So for example, we'll just do question 1 together. So if you look at the first one, uranium becoming thorium plus helium. What type of radiation is that? Alpha, beta, or gamma? Alpha, good. Ion becoming xenon plus electron, what's that? Beta. And the last one then is thorium becomes thorium, it's a gamma. Okay. Number 2. Describe a way to figure out what the radiation is, if it's alpha or beta. I want to do this one here, number 2, before you start. So imagine you have some radiation, but you don't know what type of radiation it is. Maybe it's alpha, or maybe it's beta. You don't know which. There is a simple way to test. What you do is you put a magnetic field here, north and south. Now, we use the left-hand rule here. Okay? So, isn't it? Left-hand rule.
This is the right hand rule.
Ah, flip. Should I? Did I say the right-hand rule? Hang on. Excuse me. Let me see. Is it the right-hand rule? Or is it the left-hand rule? Now I've got confused. Please mix the two up. But I guess I said right-hand there, so I must have checked it before typing it. You have the right-hand grip rule, which is for that. Then you have the left-hand rule. The left-hand rule is for calculating force, isn't it? Flip's sake. The left-hand rule is when you want to calculate the force. And the right-hand rule is when you want to calculate the current. So the left-hand rule is for the force and the right-hand rule is for the current. So I actually wrote the wrong one there. I was right the first time. It's the left-hand rule here. Okay, so just change it to the left. Right, so you remember here you have force, which is what we want. Okay, field and current. So here the field is pointing down. Okay. Now alpha is positive, isn't it? So the current is to the right for alpha, and for beta it's a negative. The current is to the left. So let's look at alpha first. So if the current's going forward, which way is the force? Into the page. And if the current is going backwards, which way is the force? Out of the page. So what that means is alpha, when it hits this field, will turn in left and beta will turn right. So this is the way you can tell what type of radiation you have. You know, if you have something with radiation coming out of it, like here, there's radiation coming out, and you put a magnet above it, so north-south. If the radiation turns this way, you have alpha, and if it turns this way, you get beta, because of the charge. Okay, so I'll just write here, alpha will turn into the page, and beta will come out of the page. So we can sort this way. We can split the alpha and the beta. Okay. I just wanted to do this example because it was in the exam, I think. They said, describe a simple way to separate alpha and beta, or something like this. So, because alpha and beta have charge, I mean, another way you could do it is like this. If you have a plate here which is positive and negative, and your radiation comes in, alpha has a positive charge, so will it move up or down? It'll move down. So as long as the plate's not too big, what you can do is you can try and pull it down a little bit, so when it comes out, it's moving downwards. You don't want it so big that it hits the plate. That would be, then you don't capture it, So you could do it like that. Moves down, and then beta. Beta is negative, so it would come in and try to get pulled up to this plate. Yeah, there's a couple of ways to do it. Is that okay? Okay, so I want you to start from number 3 for a few minutes. Actually, we did number 3 already, the uranium. That was the example I did. So start from number 4. Now, do you see that symbol in number 4, the V? Do you see it? That's another symbol for gamma. Maybe you want to write that in your book. Another symbol for gamma. Yeah, that's the alpha 4-2.
Oh, okay.
So I'm actually telling you in number 4 that there's no beta released. There's only alpha and gamma. So you can balance that, yeah?
But it'll be only 4 and 2.
Oh, definitely 4 and 2. Yeah. So, but what I don't tell you, Andek, is how many of them you have. So, like, maybe you do only have one of them, but maybe you could have like 6 of them.